You left comments about the analog selector switches I made in a previous video, so I redid them the right way, according to you. Because you were right. Welcome back to Cloud42. I'm James. I'm still working on the software for the surface grinder automation project. It's complicated for a whole variety of reasons, not the least of which is safety. I'll be putting out another video soon showing my progress. In the meantime, I'm posting more of the day-to-day details on the Patreon forum. It's been a fun conversation and I've learned a few things from it. I've also learned a few things from the comments that viewers have left on the previous videos. After I posted the video showing how I soldered surface mount resistors onto the terminals of a rotary switch to make an analog selector for the control panel, I got a number of comments pointing out two problems with doing it that way. First, viewers pointed out that over time, mechanical shock from the movement of the switch will probably crack the resistors. They were really intended to be soldered to a PCB, and mounting them in free space like I did subjects them to mechanical stress they weren't intended to handle, and that's absolutely right. And second, since two of the switch positions were outputting the maximum and minimum possible analog voltages, it isn't possible for the software to detect a broken wire. Depending on which wire breaks, the switch could just appear to be in the maximum or the minimum position, so we need to deal with that as well. Now, the right way to do this is with a small PCB on the back of the switch. And these days, that's pretty fast and inexpensive to do, so that's what we're going to do today. And while I'm at it, a simple project like this is the perfect opportunity to try out the electronics design features in Fusion. I haven't used them before, at least not for anything serious, so we'll give that a try as well. This is the switch that I used for the analog selector. You can see the part number there. This one is made by Grayhill, and I picked it out, even though it's kind of an expensive switch, it's a really high quality switch, and I really like the feel of it. I like, how rugged it is. I like the 1/4 inch or 6 millimeter shaft on it. It feels good, and it looks to be pretty durable. The less expensive switches that I bought off of Amazon were just awful, and I finally went to a real electronics supplier and got a decent switch. Now you can see this has solder lugs on the back for connecting wires, and that's going to present a little bit of a challenge, but it does have a flat surface, so we should be able to surface mount this onto a PCB with that center pin sticking through a plated through hole. Now they do actually make a version of the switch that's PCB mountable that has through hole pins, but at the time I started this project, nobody had them in stock, and they were out 12 weeks if you wanted to order them. They can only be ordered from the factory in lots of 25, so we'll just continue with the solder lug version. I have a model of the switch itself that I downloaded from the manufacturer. This one actually might have been downloaded from Mouser where I bought it. They just have free models that you can download and use for your designs, and I used this when I designed the control panel. You can see I've sketched on this and added some alignment lines to locate specifically where the different positions are, because the flat isn't lined up with the actual switch positions, and I wanted to be able to have some markers that I could use to align this when I put it into a design so that the knob would point in the correct direction. I brought that 3D model into a new design and sketched and drew out the PCB that I want to make. So this is just to define the PCB outline. There's no electronics design going on here. This is just a 3D model. This is a typical 1.6 millimeter thick PCB, and I just designed this with a sketch to lay out about the size that I thought I wanted. For scale, this is about 16 millimeters wide, so this is a relatively small PCB, but it shouldn't be too small for most board houses to handle. Now that I have the PCB outline designed, I can actually just select that face, and I can go up here to Create and say Create PCB. And there are a couple of options here. I haven't played with this very much. This is kind of my first real design in Fusion, but you can create an associative PCB that will create a link between the model and the electronics design so that you can make changes and it'll update, or you can create one that's independent and just use that as the PCB outline. And again, I haven't played with this very much. I went ahead and just created the associative PCB and created an electronics project for this switchboard. I'm not going to go through and do a full tutorial of using the electronics design in Fusion 360. That might be something that would be interesting to do for a future video. But for now, I'll walk through and show you the basic steps and what I did to design this board. Now, the first thing I needed was a footprint for the switch, because nobody publishes a footprint for mounting a solder lug switch surface mount onto a PCB. So that was something I had to create for myself. So in Fusion, you create what's called a library, and I've created an electronics library here that has a single component in it. And this component has a few things associated with it. It has a symbol and a footprint. So the first thing is a symbol, and you just draw this up. It's just a box, and then you put pins on it. And I've got 11 pins here because there are 11 pins on the switch. Of course, the variant I'm using is only a 4-pin variant, so only the first 4 pins are active, but the rest of them are present. So I went ahead and put those into the symbol. Then after you have the symbol defined, you can create a footprint. And this is the footprint. It's just a series of 10 pads in a circle. I've got some nice silk screen here. I've got a mark showing where pad 1 is. And then I've got a through hole pad in the center that is large enough to pass the pin on the bottom of the switch. Neat little tip here for laying out these pads in a circle. I thought I was going to have to do it, and I actually had a spreadsheet put together, and I was going to use the sine and cosine values and figure out the coordinates of these. But you don't actually have to do that, because you can just place one pad, and then up here under place, you can say pattern. You can select a circular pattern, and then you can go in and say how many you want, and it'll actually lay those out in a circle. So there's 10 laid on top of the 10 that are already there. I don't actually want to do this. Let me back out. I don't actually want to modify this. But that makes it easy to lay stuff like this out. I did just measure the switch with calipers and figure out about where I wanted this to be, but it's pretty easy to go back and use the 3D model to verify that the pads and the pins are going to line up before you actually make the boards. And then after you have the footprint designed, you can go in and associate a 3D model with that footprint and position it correctly. So in this case, we can see the outline of the pads, and we can see the way the component lines up on those. So now if we design a PCB and use this component, we'll place the footprint on the board, and then it will automatically include the 3D model when we output a 3D model of the completed PCB. And then the last step that's required to actually make this usable in a design is to go back up here to the component, click the connect button, and then actually map all of the pins to pads. And here I would have had a list of pins and pads, but I've already associated all of those. So the $1.1 is pad 1, the $1.6 is pad 6, and I've gone through and actually associated these so that electrically the symbol and the footprint line up. So if you connect something to pin 9 on the footprint, the system knows that that needs to be connected to pad 9 on the PCB. And in this case, it's a really simple one-to-one mapping. There's all kinds of more complex stuff you can do here, though. Pretty much all PCB design software works the same way. You start by selecting components and creating a schematic. Then you move from the schematic to laying out the PCB, and then it can generate the output files to have the PCB manufactured, and in this case also 3D models that you can put back into your other designs. Let's start by looking at the schematic. If you saw the previous video about creating the first version of the analog divider, you know that the way this works is I've got a ground and a 24-volt input, and then I've got a resistor ladder set up as a divider to create separate voltages, and then the selector switch just selects which one of those voltages is returned on the common pin here. So in this case, I'm working with a 24-volt supply, and I would like to have 10 milliamps flowing through the circuit. And so that means that I need a total of 2400 ohms of resistance, and so all of these values add up to 2400. And it makes the math really convenient because at that point, 100 ohms equals 1 volt of drop at 10 milliamps, so I can very easily choose which voltages I want here. So pin 1 is the ground, and so if I've got 200 ohms here, this first one will be at 2 volts, the second pin will be at 4 volts, the third at 6, and the fourth at 8, and the remaining 1600 ohms take it up to 24. Now you'll note a couple of things going on down here. One is there is no direct 1600 ohm resistor that I could use, or if I wanted to do something a little bit different with this, I wasn't confident that I was going to be able to get one resistor that had the value I needed, so I did this as two resistors in series. The other thing you can see is that for this last resistor, I have two devices wired in parallel. I'm only going to populate one of those resistors, but the reason I did it this way is because most of these are going to be small form factor resistors like 0805, and I wanted to have the ability to use a much larger resistor like a 1206 for this last one. Because this is a 1300 ohm resistor and will have 10 milliamps flowing with a 13 volt drop across it, this resistor is going to dissipate more heat than the others, and I wanted to be able to use a larger package that would be able to handle that heat dissipation more easily. So when I selected the components from the built-in library to bring in these resistors, all of these are 0805, and this last one is a 1206. The other difference you'll note here from the previous design is that this pin 1 is not actually connected to the ground input. It's actually connected to this first divider position. So pin 1 is at 2 volts. If for some reason the 24 volt wire got broken, all of these would be at 0 volts. And the software would be able to tell because it's not expecting anything to have a 0 volt input. It's expecting 2, 4, 6, or 8. So if the ground got broken and everything went up to 24 volts, or if the power line got broken and everything went to 0, then the outputs here would be distinguishable from a correctly functioning switch. And that just adds another measure of safety to the system. There's nothing particularly safer about the electronics here, but it allows the software to detect more error conditions. With the schematic done, we can then come over to the Validate tab and run an electrical rule check on it. And it'll go over the schematic and look for common kinds of errors. It has noted that I didn't assign a value to R6. That's fine. I'm going to leave R6 unpopulated. But this can detect all kinds of problems, like if you have power lines on components that where the pin was actually marked as a power input and you haven't connected it, it can detect various kinds of electrical rule violations. There's a whole rule set behind this, and that can be customized. But for most use, this just provides a simple little check. If you're using library components, it can tell you when you've messed something up. Pushing this schematic over to the PCB document then gives us a pile of footprints that we have to place. And I've already placed those here on the board. I've got the footprints for the switch on the top of the board, and I have this header set of pads. They're through holes, so those are on both sides. And then I've got all of the resistors on the bottom of the board. And I've laid that out. And you can see this is all connected, and I've got some vias in here where I'm switching layers. Now, as far as choosing trace widths and via sizes, the defaults are pretty small. I bumped these up a little bit larger just to make the board easier to manufacture. Depending on who you're using to manufacture it, the larger hole sizes can be cheaper, or more accurately, you may have to pay a premium for very small vias. So I bumped these up to some nice conservative values. In this case, the vias are still on the small side. Those are 16 mils, and the traces I think are 16 mils. And those are good safe values that aren't going to run you into extra costs with most PCB fabs. And then just like with the schematic, we can come over here to the Rules tab and we can run the design rule check, and it will analyze the design and show us any errors. And I don't have any errors. When I first started the first pass through here, these vias were pretty close to the pads. In fact, there were some places where there was a via that was partially under one of the surface mount pads, so it flagged that. That doesn't always matter, but it might depending on what you're trying to do and depending on how dense the board is. So I moved things around and solved all of those, and then that gives me a PCB design that I can then output and have manufactured. And with the board designed, we can just click here to push that to the 3D PCB. In this case, I've already done that, and we have that document here. And so we can see this has got the footprint that has the 3D model associated with it. In this case, the resistors also had 3D models associated with them, along with this connector. So this all looks right to me, and since I know that this model is accurate, I can see that my clearances on those pads all look pretty good. This looks like something that I will be able to solder, so we can go ahead and export this and have the boards manufactured. We can also take that model and round trip it back into the original control panel design, and see how that PCB is going to fit. And this looks fine to me. I probably don't want to use those right angle pin headers, but I looked around on Amazon and discovered that you can buy 0.1 inch pitch or 2.54 millimeter pitch screw terminals. So I've got some of those ordered, and I will solder those on when the boards arrive. To actually have these boards manufactured, I can just come over here to the manufacturing tab, and there's a button here to export Gerber, drill, assembly, and drawing files. Click that, tells me what it's going to create, and then you can just upload that Gerber file to your favorite PCB board house, and they should be able to create it. Note how I said PCB board? I said that just to annoy people. Go ahead and put your rage in the comments. Now, this is not sponsored. JLC PCB has contacted me about sponsorships. I've never replied to them. I just use them because they're convenient. I probably am an idiot for turning down their money, but like I said, this is not sponsored. So you can choose from a bunch of different board materials. This is a 2-layer board. It's automatically got the dimensions in here, and we can decide how many we want. And with this design, 5 of them, it comes out to $2. You know, it's some kind of a promotional thing. But I found that often you can get quite a few boards for not too much more money. In this case, 20 boards is $4.60. You know, so it's pretty easy to go ahead and order a bunch. There you go, 25 is only $4.70. Now there will be a big jump in price at some point, but you can poke around here. So there we go, 50 is again $9. So it's pretty easy to order quite a few of these things if you need them. Now, there are a couple of things that I do like to change. I am going to go to lead-free solder. So this is hot air solder leveling. You can also get it with a gold finish, and that raises the price a little bit, but it's still pretty reasonable for this. Now, I already placed my order, and for 25 pieces, it looks like I paid $13.39 and then an additional $18.37 for shipping. So $30, and it took about 7 days from the day that I placed the order to the day that it actually arrived on my doorstep. It took about a week, so that works for me. No matter how many times I do this, I am always caught off guard by just how small the PCBs are. I do my work on a 32-inch 4K monitor, and I have it all blown up nice and big, and you just lose track of the scale. These look pretty good. This is the lead-free hot air solder leveling. You can see all the vias are tinted. And it looks like they have increased the resolution of their silkscreen over the years. This looks really good. And the part lines up. I think these things are ready to solder. Now, soldering these things is a little bit clumsy. It's kind of hard to hold the part in place because you're placing the part from the front and also soldering from the front. But, you know, once you get it tacked in place and in the right position, it goes pretty easily. It's harder to film than it actually is to do. Then, of course, the center pin has a lot more thermal mass, so it takes more heat and time to get that hot enough to get the solder to wick in. And then it's just a bunch of surface mount resistors. And these are always fiddly. And the key here is just to use lots of flux. You can see the residue all over the board, and you can just keep going back and reheating and cleaning up the solder joints until they look the way you want. And then just flood the whole thing with isopropyl alcohol and scrub it off. And it will look pretty. And if it doesn't, you can just remelt the solder joints with more flux, go back and clean it again, and it will. As long as you have a temperature-controlled iron so you're not overheating the board, you can get nice clean results even with lead-free solder. Now you can see this particular switch is one that I had the surface mount chips actually soldered to, so there's extra solder on the legs. I reused it because these things are like $40 a piece, and I didn't want to buy any more than I needed to. But this looks great. And of course, they fit back into the control panel exactly as they did in the 3D model. Go figure. It kind of amazes me just how much it looks like the 3D model. I love this kind of stuff. Of course, it doesn't matter how it looks if it doesn't work. So I've got this wired up to a power supply. I have this set to 24 volts. And if I turn it on, you can see that it's drawing about 11 milliamps. It should be about 10 milliamps. And I expect this is just an instrumentation error. The last digit isn't that reliable. I've got this hooked up to a 6.5 digit multimeter. You can see it was outputting 2 volts, 4 volts, 6 volts, and 8 volts. Pretty much right on the button. That is exactly what we want.
Now, if you manipulate this switch, because it's a non-shorting switch, you can get it to a position in between, and it just floats. So on the clear core, that'll float low to 0 volts and should read as a broken wire. I can go ahead and increase the sampling period on this so that we can see all the digits this meter is capable of. And you can see these voltages are pretty close. These are just 1% resistors out of a selection book that I bought off of Amazon, and this looks really good. In the firmware for the ClearCore controller, I went ahead and extracted the concept of this analog selector switch out into a separate class. So this class is just initialized with an analog input, and then it has the ability to get the switch position. And there's a couple of things here. You'll note that instead of returning an integer, this is returning an optional integer. Now, what I really wanted to do was use the standard optional template, but that's actually not available in Arduino. Arduino only operates with up to C++11, and it doesn't actually have all of the features of C++11 either. So instead of using that, I fell back and I just created my own optional template class. So an optional just contains a value and a Boolean that says whether there is a value present or not. So in this case, if the voltage is less than 1, then I know that there's a broken wire, and I just return an empty optional saying there is no value for the analog switch. If it is greater than 1 and less than 3, I return 0. If it is greater than 3 and less than 5, I return 1. So I can return my values 0, 1, 2, and 3, or I can return an empty optional if for some reason I can't get a value from the switch. Maybe it's between positions because this is a non-shorting switch, or maybe a wire is broken, or maybe something unexpected has happened, but no value is available. Now, it turns out that just creating an optional template type in C++ is a lot more complicated than you might think. I'm trying to do the right thing in here with both copy and move constructors and assignment operators, but things can get out of hand quickly. I actually got it into a state where the compiler was generating code that was trying to do a conversion that it couldn't do, which led to memory corruption, which caused the ClearCore controller to crash with one of the motors spinning. Even the built-in e-stop functionality didn't stop it. I didn't even know that was possible. And to try to keep some of that at bay, I've also implemented a unit test and actually have unit tests for these. I'm just using the Microsoft Visual Studio C++ unit test framework so that I can use the Test Explorer in Visual Studio. And this definitely has some limitations. For one, I'm actually recompiling the C++ code that is intended for the ClearCore to C++ intended and run on the Windows machine in order to run the test. So it's a different compiler, and there is a little bit of risk involved in that, but it does provide a good way to test logic. And so you can't test everything, but I can at least test and make sure that the logic, for example, here in my optional class, is working properly. I will admit that I've been goaded into some of this complexity by comments on some of my videos saying, hey, you should check out these new features. They're really neat. And yeah, they really are. And I just couldn't help myself. But in general, I find, especially with embedded development, keeping things as simple as possible is the best way to go, just because debugging in an embedded platform is so difficult. I heard it said once that debugging is twice as difficult as writing the code in the first place. So if you write the code as cleverly as possible, you are by definition not qualified to debug it. Over my 30 years in the software industry, I have found that to be true.
As I said, the software development is proceeding, and there's an ongoing discussion about it in the patron forums, but this part of the project always takes longer than I want it to. If I just wanted to get the machine cycling so I can grind something, that's not particularly hard. But if I want something flexible and usable that handles all of the weird conditions the machine can get itself into and do it safely, which I do, that's a different matter. Add in that I'm trying to level up my C++ skills and use some new language features, development tools, and an automated test framework, and I've just made the project much more complicated than it actually has to be. But I've also made it much more rewarding. If you enjoyed this video, you can give it a thumbs up, you can subscribe, and you can think about supporting the channel on Patreon. Thank you for watching.